Before you dive into the next video, pause for a moment and imagine standing at the edge of existence itself. No stars, no galaxies, no space, no time, just a silent cosmic darkness holding the greatest secret of all, the moment the universe became real. If questions like what existed before everything send chills down your spine, then you're in the right place. Because here, we explore the mysteries that even the universe hesitates to reveal. So before we unlock the next chapter of this cosmic story, make sure you subscribe to the channel, hit the bell icon, and join the community that refuses to stop searching for answers. Your curiosity is the fuel, and together, we'll continue pushing beyond the limits of space, time, and imagination. Imagine everything you have ever known, every moment in history, every star that has ever burned, every galaxy that has ever shimmered in the darkness, every molecule, every atom, every quantum particle, every law of physics that shapes our world, compressed into a single point, not a point floating in space, not a point inside time, but a point that contains space, time, and the very rules by which reality operates. This point, this almost unimaginable state, is what scientists call the singularity, and understanding it, even slightly, begins to reveal the profound mystery of what may have existed 1 second before the Big Bang. The singularity is not just a small object, it's not even an atom-sized structure. It is a state where the density of the universe becomes infinite, where the gravitational pull becomes so extreme that the formulas of Einstein's general relativity break down. In normal science, when equations break, it means we have reached the limit of our understanding. The singularity is the cosmic boundary that stops even the greatest minds in their tracks. But what does infinite density actually mean? Try to imagine taking the entire Milky Way galaxy, over 100,000 light years across, filled with hundreds of billions of stars, and compressing it until it is smaller than a grain of sand. Then do that not just for our galaxy, but for all galaxies, Andromeda, Triangulum, Virgo cluster, every strand of the cosmic web, every supercluster, every particle of dark matter. Compress all of that into something smaller than the smallest thing the human mind can conceive. That is the singularity. Some say this is the birthplace of the universe. Others argue it is the graveyard of a previous one. But there is something even more astonishing. The singularity may not have existed in the way we imagine. It might be a clue that the universe had a hidden state, a deeper layer of reality before the Big Bang exploded outward. To understand why, we must think about time itself. We humans experience time as a flowing river, past, present, future. But the closer you get to the singularity, the more time behaves strangely. Locations in space become indiscernible. Seconds stretch or shrink. The very structure of space-time begins to twist. In this ultra-hot, ultra-dense state, time may not flow at all. It may not even exist, so when we say 1 second before the Big Bang, we are forced to ask whether that phrase even makes sense. Can you have a before, when time has not yet begun? Yet the question remains, because something must have happened. Something must have existed. Even if time did not tick in the way we know, some kind of state or condition must have preceded the event we call the Big Bang. The singularity itself might not be the beginning, it might be the transition point between two phases of reality. Einstein's equations describe gravity so well that we have tested them in black holes, GPS satellites, and the movement of galaxies. But when we apply those same equations to the beginning of the universe, they break completely. They predict the singularity, yes, but they also predict infinity's numbers that make no physical sense. Infinity is not a quantity, it's a sign that our mathematics is incomplete. That means the singularity is not an answer. It's a question mark, a doorway, a clue that something deeper lies underneath. So scientists turn to quantum mechanics, the physics of the incredibly small, to try to understand what might have existed before the universe expanded. Quantum mechanics is strange. Particles pop in and out of existence, energy fluctuates even in empty space, and matter behaves like both a wave and a particle. If this weirdness existed before space and time were born, then the singularity might not have been a point at all, but a quantum foam, a restless sea of energy bubbling with potential. If so, then the question becomes even more fascinating. What stirred this quantum sea? What triggered the shift from stillness to expansion? There is another school of thought that views the singularity not as a beginning but as a boundary. Imagine the face of a clock. You can move the hands backward 1 hour, 2 hours, 10 hours until you reach midnight. Midnight is not the end of time. It is simply the starting point of a new day. Similarly, the Big Bang might not have been the birth of the universe. It might have been a reset, a transition, or a transformation from something that existed before. Some equations from modern theoretical physics suggest that universes can expand and contract in cycles. Expansion, heat, cooling, collapse, then compression into a singular-like state, and then a new burst, a new Big Bang. This means that 1 second before the Big Bang might have been the final second of a collapsing universe, a finale to a previous cycle of cosmic evolution. Imagine an ancient universe, full of galaxies and stars like our own, reaching the end of its lifespan. Over trillions of years, gravity slowly pulls everything inward, galaxies drift together, stars burn out. Space shrinks at the very end, the entire universe collapses back into a super-hot, super-compressed state. Before the final moment of collapse, there is one last second, a second full of unimaginable forces, temperatures beyond anything that could be described, and densities so high that matter loses all form. That final second could be the state that existed before our universe was reborn in the Big Bang. But there is a deeper question. If this cycle is real, how many universes came before ours? 10, 1,000? An infinity? Could traces of previous universes be encoded subtly into our own cosmic microwave background, the faint leftover radiation from the first light of the universe? Some scientists claim to have found circular imprints, like scars from another cosmic age. Others are skeptical. But the idea haunts us. Our universe may carry the fingerprints of something that lived and died before us. Still, other theories paint a different picture. Instead of cycles, instead of collapse, the singularity might represent a moment when two universes touched. In string theory, our universe may exist on a giant three-dimensional brain floating in higher dimensions. If another brain drifted close, the energy released from their collision could have created a Big Bang. In this case, 1 second before the Big Bang would be the moment before impact, a silent, cosmic calm before two unimaginable sheets of reality brushed against each other. To us, it would appear as a spark of creation. To a higher, dimensional observer, it would be a simple interaction. Yet even this explanation raises new mysteries. What caused the brains to move? How long had they existed? Are collisions rare or common? Are there countless universes, each emerging from their own cosmic encounters? Then there's the most radical idea yet, that the singularity never existed at all. Some modern theories remove the need for it entirely. They suggest that quantum laws softened the universe at the earliest moments. Instead of an infinitely dense point, the universe might have begun as a small, but finite region of energy. This region could have existed timelessly, neither expanding nor contracting, in a stable quantum state. Then a sudden event, a fluctuation, a quantum transition, caused expansion to begin. In this scenario, 1 second before the Big Bang was a moment of silent balance, a cosmic stillness waiting to erupt. Picture a perfectly calm pond, its surface smooth and unbroken. Suddenly, a single ripple appears, not from wind, not from motion, but from the very fabric of the water itself. That ripple becomes a wave, the wave becomes a flood, and soon the entire pond is alive with motion. That first ripple is the Big Bang, the perfectly calm pond is the state 1 second before, but even this calm state wasn't truly empty. Quantum mechanics teaches us that emptiness is never truly empty. Even in a perfect void, particles flicker into existence and vanish instantly. Energy fluctuates, probability itself vibrates. So 1 second before the Big Bang, the universe might have been a tiny quantum universe, so small that it wasn't visible, so delicate that it could collapse or expand based purely on statistical chance. Some physicists believe that our universe is just one of many that form from such fluctuations. In this view, the singularity was not a single event, but a natural outcome of quantum laws. Universes could be forming constantly, bubble universes in a grand cosmic sea. Each bubble expands, cools, forms galaxies, creates stars and life, and eventually fades. If this is true, then 1 second before the Big Bang was simply the moment before our bubble expanded into the vastness we now see. But here's the greatest mystery: we can see back in time. Using powerful telescopes, we observe galaxies as they were billions of years ago. We can measure the cosmic microwave background from when the universe was just 380,000 years old, but we cannot see the singularity. We cannot observe anything before the first fraction of a second after the Big Bang. The universe becomes opaque, like a wall of fog. Beyond that fog is the moment of the singularity, hidden forever, at least to our current tools. Yet the human mind refuses to stop. This singularity represents the boundary of science, but also the frontier of imagination. To understand what existed 1 second before the Big Bang is to seek answers to the deepest questions humanity has ever asked. Where did we come from? Why is there something rather than nothing? Is our universe unique or one of many? Did time have a beginning, or is it an infinite loop? All of this begins with the singularity. Whether it was a real point, a boundary, a transition, a collision, a quantum fluctuation, or a doorway from a previous universe, the singularity stands as the most mysterious state in all of physics. It challenges not just our understanding of the cosmos, but our understanding of existence itself. The universe today is vast beyond comprehension. Galaxies drift apart, stars live and die, planets form, life emerges, consciousness awakens. Yet all of this came from something smaller than a grain of dust, something that held the blueprint of everything. 1 second before the Big Bang is the moment when that blueprint still existed in silence, in compression, in unimaginable density. It is the moment when the universe was holding its breath before taking its first cosmic step. We may never truly know what existed in that moment, but the pursuit of the answer is what drives science forward, and perhaps that pursuit is just as important as the answer itself. Because every time we ask what happened before the beginning, we push the boundary of knowledge a little further. We take one more step into the unknown. We stand at the edge of time and peer into the abyss, knowing we may never reach the final answer, but daring to chase it anyway. And maybe in that pursuit, we discover something even more profound, not just how the universe began, but why we are here to ask the question at all. Imagine the universe not as a one-time event, but as a living, breathing entity, a cosmic heartbeat that expands, collapses, dies, and is born again. Imagine that the Big Bang was not the first beginning, not the ultimate origin, but simply the latest chapter in an infinite cosmic story that stretches far beyond the reach of human imagination. This idea, known as the cyclic universe, challenges our deepest assumptions about time, creation, destruction, and eternity itself. And at the heart of this idea lies a profound possibility: that 1 second before the Big Bang was the dying breath of a previous universe. To understand this, You must picture the cosmos not as a straight line with a single beginning, but as an endless circle. A cycle, a rhythm, a beat, just as stars are born from the ashes of older stars, and planets emerge from the remains of ancient explosions, the universe itself may be reborn from its own collapse. This is not creation from nothing, it is creation from transformation. The idea begins with a simple observation: the universe is expanding. Galaxies are racing away from each other, space itself is stretching, and the farther away an object is, the faster it seems to move. This expansion began with the Big Bang nearly 8 billion years ago, but what happens in the far future? What happens when the universe grows so large, so spread out, so diluted, that gravity can no longer hold galaxies together? One possibility is that the expansion continues forever. Another is that the expansion slows, stops, and reverses. If it reverses, the universe begins to collapse, shrinking inward over trillions, then quadrillions of years. Galaxies would drift back toward each other, stars would collide, black holes would merge, temperatures would rise. Space would contract, and eventually the entire universe would condense into a state of unimaginable heat and density, the very state we associate with the Big Bang. In that instant, the death of one universe becomes the birth of another. The last second of the previous cosmos becomes the first second of the next. This cycle continues, perhaps endlessly, each universe giving way to another in a grand cosmic sequence. There is a haunting beauty in this idea. It suggests that everything ends, but nothing is lost. It implies that our universe carries within it the echoes of those that came before. It tells us that creation and destruction are not opposites but partners in an infinite dance. But the cyclic theory goes even deeper. It proposes that the last moment of the previous universe, the final heartbeat before collapse, may determine the conditions of the next. The way that universe collapsed, the forces that shaped it, the distribution of its matter, its cosmic DNA, might have influenced the universe we inhabit today. 1 second before the Big Bang, in this vision, was not an empty void. It was a universe in its final moments, gathering itself into a single white, hot point, preparing to explode outward once again. Consider what that final second might look like. Picture a universe unimaginably old, so old that stars no longer exist. Most have burned out or collapsed into black holes. Galaxies have merged into gigantic clusters. These clusters have merged into even larger structures. Eventually, after unimaginable stretches of time, everything collapses inward. At the end of this collapse, all matter is compressed. Temperatures rise beyond the limits of physics, gravity becomes overwhelming, the fabric of space tightens. Atom after atom is crushed, particle after particle falls into the collapsing remnant of everything. And then, right before total collapse, there is one last second, a second filled with such intense conditions that the laws of physics nearly tear themselves apart. This final second might be the blueprint for the next universe, and then the collapse completes, and the next Big Bang emerges. There is an elegance to this theory, but it is not just philosophical. It has mathematical foundations drawn from Einstein's equations and modern cosmology. When applied to extreme conditions, general relativity allows for the universe to expand and contract cyclically. Yet relativity alone does not explain how the universe rebounds after collapse. For that, scientists turn to quantum mechanics. Quantum theory suggests that at extremely small scales near the Planck length, space and time begin to behave in strange ways. Forces unify, boundaries blur, singularities may soften. Instead of collapsing into an infinitely dense point, the universe might reach a minimum size and then rebound. Quantum pressure, or what physicists call quantum gravitational effects, may prevent a true singularity. That means the universe would never fully collapse to zero size. It would reach a tiny, but finite, state, and then bounce outward.
This quantum bounce could be the mechanism behind each cycle. The Big Bang we know might simply have been the big bounce of a previous cosmic cycle. If so, then the universe before ours might have had its own galaxies, its own stars, its own evolution. It might have been unimaginably different or uncannily similar, and everything that existed in that universe would have been compressed into a single moment before rebirth. Imagine for a moment that in the final second of the last universe, there were remnants of civilizations that had advanced far beyond our understanding. Perhaps they lived in distant galaxies, trillions of years old. Perhaps they discovered the impending collapse and witnessed the final contraction of their cosmos. Their final second, their final moment, would also be the moment before our universe began. We will never know their stories, their discoveries, their hopes, their end. But in a cyclic universe, their universe gave birth to ours. Their existence is part of our cosmic ancestry, even if no trace remains. Other versions of the cyclic theory propose a different mechanism entirely. Instead of collapsing, the universe may expand forever, growing colder and emptier until all activity ceases. At that point, quantum fluctuations may trigger a new region of space to begin expanding again, creating a new universe from the ashes of a cold, dead one. In this model, the last second before the Big Bang might have been the last second of a universe that had spread itself so thin that it could no longer sustain stars, planets, or structure. A cosmic freeze giving way to a new cosmic fire. And then there is the idea that the universe undergoes cycles not of expansion and collapse, but of energy phases. According to some modern theories, such as those related to string cosmology, the universe might have existed in a cold, static state for unimaginable lengths of time. Then, due to fluctuations in higher dimensional fields, the universe could undergo a dramatic phase transition like water suddenly turning to steam. This transition could trigger a new Big Bang. The second before the Big Bang would be the moment before this transition, calm, quiet, and cold, followed by an eruption of expansion and heat. What makes the cyclic idea so compelling is that it solves some of the deepest puzzles in modern physics. It addresses why the universe is so uniform in every direction. It offers an explanation for the arrow of time. It even hints at why fundamental constants seem finely tuned. If the universe has been cycling indefinitely, there may have been countless opportunities for the constants of nature to settle into stable values. In a single, beginning universe, this fine tuning seems miraculous. In a cyclic universe, it seems inevitable. But the cyclic theory is not without its mysteries and difficulties. One major question is entropy, the tendency for systems to become more disordered over time. In each cycle, entropy should increase. So how does the universe reset its entropy with each new cycle? Some physicists propose that during collapse, entropy is squeezed out of our universe into higher dimensions. Others suggest that each cycle is far larger than the last, making entropy less relevant. Some even argue that the universe does not need to reset entropy because each cycle represents an entirely new thermodynamic environment. There is also the question of evidence. If a previous universe existed, could we see any trace of it? Some researchers believe that faint circular imprints in the cosmic microwave background radiation, the leftover glow from the earliest moments after the Big Bang, could be the scars of collisions or structures from a previous cycle. Others argue that these features are simply random fluctuations. The debate continues, and every new satellite and telescope brings us a little closer to the truth. Yet even without definitive proof, the cyclic idea resonates deeply with our sense of cosmic rhythm. After all, cycles are everywhere in nature: the seasons cycle, stars cycle, life cycles, even atoms move in rhythmic patterns. Why should the universe itself be any different? And this brings us back to the moment that matters most, 1 second before the Big Bang. In the cyclic model, this second is not empty, it is full of everything the previous universe once was. Full of heat, full of pressure, full of contraction, full of a cosmos in its final moment. In that second, the fate of the next universe is sealed. The energy densities, the patterns of quantum fluctuations, the physical laws that will shape galaxies and stars, all of it is encoded in that moment of collapse. We often imagine the Big Bang as the beginning, but in a cyclic universe, it is simply the middle of an endless story.
There was a universe before ours, and there may be one after. We are part of a cosmic lineage stretching far beyond our ability to perceive.
We are the children of a previous creation, and the ancestors of a future one.
And perhaps the most humbling thought is this: one day, trillions and trillions of years from now, when our universe collapses into its final second, it will not be an end.
It will be the beginning of another universe, another expansion, another journey.
Just as we wonder about the universe before ours, another form of life, if life ever arises again, may one day wonder about us.
In that grand cycle, the universe becomes a story without a final chapter, a flame passed from one cosmos to another.
The Big Bang is not the start of everything, it is a pulse, a beat, a spark in the eternal rhythm of creation.
1 second before the Big Bang is not the silence before the beginning, it is the last note of a cosmic song that began long before we existed and will continue long after we are gone.
Imagine for a moment that our universe is not alone.
Imagine that the cosmos we see, the galaxies, the stars, the planets, the space between them, is nothing more than a single bubble floating in a vast, unseen ocean. And imagine that this ocean is filled with countless other bubbles, each one its own universe, each governed by its own laws of physics, its own dimensions, its own timeline, its own beginning, and
its own end. What if the Big Bang was not the beginning of everything, but simply the moment when our bubble collided with another in this infinite multiverse?
This idea is known as the multiverse collision theory, and it introduces one of the most astonishing possibilities ever proposed, that 1 second before the Big Bang, two universes touched. To understand this, we must first let go of the familiar picture of the universe. In our daily lives, we think in 3 dimensions: height, width, and depth, plus the dimension of time.
But cutting-edge physics suggests that there may be far more dimensions than these.
According to string theory, reality is woven from tiny vibrating strings that require 10 or even 11 dimensions to fully operate. Some of these dimensions are too small to perceive, others might be enormous, and within these extra dimensions, entire universes may float like sheets, what physicists call brains. Short for membranes. Imagine each universe as a gigantic, invisible sheet suspended in a higher, dimensional space.
These brains can move, they can wobble, they can stretch, and sometimes they can collide. In this vision, the Big Bang was not an explosion from nothing.
It was the violent aftermath of 2 brains crashing together. When they hit, the enormous energy of the collision would ignite a blast of heat and light powerful enough to create everything we know: space, time, particles, atoms, galaxies.
The collision would release unimaginable energy, heating the universe to temperatures beyond comprehension.
This is the Big Bang, but it didn't come from a beginning, it came from an impact. Now picture what existed 1 second before that event.
There was no space as we know it, no time in the human sense, no galaxies, no stars, no matter, but there were brains drifting silently through the higher, dimensional expanse. Their surfaces rippling like cosmic fabric, their presence subtle yet immense. 1 second before the Big Bang, these brains were on a collision course, drawing closer and closer until their surfaces brushed. The moment before impact, everything was calm, no heat, no light, but the potential for creation was building like tension in a drawn bowstring.
When the collision happened, it wasn't the birth of the universe, it was the release of this cosmic tension. The energy released spread across the brains, creating a shockwave of cosmic fire. In this picture, the Big Bang was not an explosion in space. It was the creation of space itself as the brain heated and expanded.
What we call the beginning was, in fact, a transformation triggered by a cosmic event in a higher, dimensional world.
This raises a profound question. If our universe is one brain, how many others exist? Tens, hundreds.
An infinite number. If collisions can happen, have they occurred countless times before? Will they happen again?
Could our universe once have collided with other universes, leaving imprints deep in its earliest light? Some scientists believe the answer may be yes. The cosmic microwave background, the faint afterglow of the Big Bang, contains subtle patterns, fluctuations in temperature across the sky.
Several researchers have suggested that circular anomalies in this background could be the scars of past collisions.
Imagine two universes brushing against each other, sending ripples across their surfaces. Those ripples might still be faintly visible today, billions of years later. Not everyone agrees. The data is unclear, debated, and mysterious, but the possibility lingers. Our universe may bear the fingerprints of ancient cosmic collisions. The multiverse collision theory also offers an answer to one of the deepest puzzles in physics: why the universe is so uniform in every direction.
Normally, distant regions of space should look very different because they could never have communicated with each other. Yet the universe appears astonishingly smooth, as though everything was perfectly coordinated.
If the Big Bang was triggered by a brain collision, that impact would instantly heat the entire brain evenly, creating the uniformity we observe. The multiverse collision theory does not just offer a story, it offers solutions. But as with all great mysteries, understanding creates new questions. If our universe formed from a collision, what happened to the other brain? Did it survive? Did it shatter? Did it pass through ours, continuing silently into the higher dimensional space? And if it survived, does it contain its own galaxies, its own physics, its own beings wondering about their own origins? The haunting possibility is that there might be life in other universes, but we will never meet them. Not because of distance, but because they exist in different dimensions entirely. Now picture the moment before the collision again. Two brains drifting closer, each carrying its own vacuum energy, its own properties, the entire destiny of our universe determined by the angle, the speed, the precision of the collision. A tiny difference in the collision could have changed the laws of physics, the mass of the electron, the strength of gravity, the balance between matter and antimatter. Even a minuscule variation could have made our universe unable to form stars, planets, or life. This means everything we know, every atom, every heartbeat, every thought, may exist because of the exact way two universes touched. Think about that. The conditions for life may have come from geometry in higher dimensions. The multiverse collision theory also gives us a new way to think about time. In the standard Big Bang theory, time begins at the Big Bang. There's no before, because time itself emerges from the fireball. But in the collision picture, time exists in the higher, dimensional space even before impact. The brains move through time. Their collision happens in time, so suddenly the question, what happened before the Big Bang, becomes meaningful. The Big Bang was simply one event in a timeline that stretches farther back than our universe. But what was that timeline like? What drove the brains together? Were they always drifting? Were they created by something even larger? Did they collide before? Will they collide again? Some theories suggest that collisions may happen repeatedly. Brains oscillate toward and away from each other, colliding at intervals and creating new universes each time. This creates a new kind of cyclic universe, not one that collapses and rebounds, but one that is periodically renewed by impacts between universes. If that is true, then the Big Bang was not the beginning, but one chapter in a long history of cosmic collisions. Our universe may be one generation in an infinite family tree of universes, but the collision theory does not require cycles.
Brains may drift indefinitely, moving unpredictably within higher, dimensional space. Collisions may be rare, random, and scattered. Universes may form only when the conditions are right, when the motion and geometry of the brains align perfectly.
In this scenario, our universe might be one of countless universes born from chance interactions in an endless cosmic expanse. Some physicists imagine universes stacked like pages of a book, flat brains parallel to one another. In this model, the distance between universes is measured not in kilometers or light years, but in dimensional separation. If two pages were to bend and touch, a Big Bang might occur at the point of contact. The entire universe could form from a single cosmic touch point. 1 second before the Big Bang, the pages of the cosmic book were drifting closer, pulled by forces we do not fully understand. The idea is strange, but strange ideas have described our universe before: black holes, quantum tunneling, particles existing in two places at once, space expanding faster than light. All once seemed impossible. Now they are part of modern physics, and perhaps the strangest idea of all is this: the collision theory suggests that the Big Bang was not special. It was natural, it was inevitable. If brains drift endlessly in higher dimensions, collisions will eventually happen. New universes will emerge, reality will keep unfolding, creation becomes a repeating process, built into the structure of higher dimensional space.
This transforms the philosophical question of existence. Instead of asking, why did the universe begin, we begin to ask, what is the nature of the space in which universes collide?
The mystery deepens, but so does the wonder. Now imagine the exact moment of the collision. The brains rush together. For an instant, the separation between universes vanishes, energy flows, light bursts into existence.
Temperature skyrockets, particles form from pure energy, time inside the universe resets, space explodes outward. The brains may rebound, separate, or pass through each other, but the new universe begins to expand, carrying within it the memory of that first, violent moment.
Then imagine the second before it happened, a moment of perfect stillness, no galaxies, no stars, no heat. Just endless dimensional space and two brains drifting silently toward destiny. In that second lay the seeds of all creation.
Every atom in your body, every star in the night sky, every galaxy in the cosmos, every heartbeat, every moment of human history.
All of it existed only as potential, waiting for the collision that would unlock it. The multiverse collision theory does not merely expand the story of the universe. It explodes it. It suggests that creation is not rare, it is not unique, it is not miraculous in the way we once thought. Instead, creation may be woven into the deep structure of reality itself, something that happens naturally, repeatedly, and endlessly. If this idea is correct, then somewhere, right now, in dimensions beyond our perception, two other brains may be drifting toward each other.
Another Big Bang may be waiting, another universe, another reality, another possibility.
And just as we wonder about the universe that came before ours, some future consciousness, born billions of years from now in another universe, may wonder about the event that created their world.
They may look back at the oldest light in their cosmos and search for patterns, ripples, or scars that hint at a cosmic collision long before they existed.
In that eternal chain of universes, the distinction between beginning and end dissolves. Creation becomes a pattern.
Existence becomes a tapestry, and the Big Bang, our Big Bang, becomes one shimmering thread in an infinite cosmic fabric.
1 second before the Big Bang was not nothing, it was the silent moment before two universes met, and from that meeting came everything.
Quantum fluctuation theory is one of the most extraordinary ideas ever proposed by modern physics, not because it provides a neat, simple answer to the origin of the universe, but because it pushes human imagination into a realm where logic bends, intuition fails, and reality behaves in ways that seem impossible.
When scientists speak about quantum fluctuations giving rise to the universe, they are not referring to a physical explosion inside space.
They are proposing something far more radical, that the universe emerged from a state that had no space, no time, and no physical laws as we understand them.
To expand this idea is to explore the very frontier of existence, an arena where the fabric of reality trembles, flickers, and dances with possibilities too small to see and too strange to fully. Imagine 1 second before the Big Bang. In this scenario, the universe did not sit quietly waiting. Instead, reality was in a suspended, formless condition, a state scientists call the quantum vacuum. The word vacuum in everyday life means empty space, a region with nothing inside it, but the quantum vacuum is not empty at all.
It is a dynamic, boiling ocean of energy where particles appear and disappear constantly, flickering in and out of existence on timescales so short that they cannot be observed directly.
To understand this, imagine watching a perfectly still pond. To your eyes it looks motionless, silent, untouched. But beneath the surface, thousands of microscopic events are happening. Chemical reactions, molecular vibrations, tiny shifts in pressure. In the same way, the quantum vacuum appears empty, but it is alive with fluctuations, bursts of energy so small and fleeting that they resemble sparks from an invisible fire. According to quantum mechanics, these fluctuations are not optional features of the universe, they are required.
They are built into the fabric of reality. They are the universe's way of ensuring that energy and probability never fall to absolute zero.
Even nothing cannot truly remain nothing. It trembles, it fluctuates, it breathes with potential. And this potential, this ever-present flicker, is what some scientists believe eventually erupted into the Big Bang.
In this view, 1 second before the Big Bang was not a dramatic moment.
It was simply another instant in an infinite sea of potential, a calm before a cosmic storm that had been brewing in silence for eternity. But this raises a question: how can a universe arise from nothing? The answer lies in understanding what nothing means in physics. It does not mean the absence of everything. It means the absence of classical matter and space, but not the absence of the quantum fields that underpin all existence.
These fields are always present, even when they appear to be empty. They are fundamental layers of reality, like the canvas upon which the universe is painted. And because these fields can fluctuate, they can create tiny bursts of energy that behave like miniature universes.
Most collapse immediately, vanishing back into the vacuum. But the theory suggests that once in a while, one of these fluctuations can become stable and expand instead of collapsing. If that expansion accelerates rapidly, it becomes a universe, our universe. To make this even more astonishing, the laws of physics, including quantum mechanics itself, do not forbid this. They allow mathematically for an entire universe to arise from a point of zero total energy. Matter and energy exist, but they are balanced by the negative energy of gravity, meaning the universe can sum to zero. It is like taking $100 from a bank account but simultaneously generating a debt of $100. The net change is zero, even though money moved. In this analogy, the universe is the money, and gravity is the debt that balances the cosmic books. So the universe may be a grand cosmic balancing act where existence costs nothing. If the universe came from nothing, It may have required no external push, no supernatural intervention, no initial trigger beyond the inherent instability of the quantum vacuum. This concept forces us to rethink the nature of existence itself. Instead of asking, what created the universe? Quantum fluctuation theory asks, why should there be nothing instead of something? Because mathematically, something is easier, more natural, than absolute nothingness. Absolute nothingness is unstable. Something will always emerge from it, and in this case, the something was an expanding bubble of space-time that grew into our universe. Imagine this quantum vacuum not as a dark void, but as an infinite ocean of invisible energy. At every point in this ocean, the surface is rippling, forming tiny waves that rise and fall. Most waves are small and fade instantly, but one wave becomes larger, grows stronger, and instead of collapsing, it expands. This expanding wave is what we now call the universe. It stretches, inflates, and within fractions of a second becomes enormous. Then it cools, forms particles, atoms, stars, galaxies, planets, and eventually life, all from a tiny burst of energy emerging from a timeless, spaceless quantum sea. The idea is so strange that it challenges every instinct humans possess. We are used to thinking in terms of cause and effect, beginnings and endings, creators and creations. But quantum mechanics does not follow the rules of human logic. It follows the rules of probability, uncertainty, and mathematical stability. The quantum vacuum does not need a cause. It simply exists. It is eternal, beyond time, beyond location. If time began with the Big Bang, then the quantum vacuum exists outside time. It is not before the Big Bang, because before has no meaning. It is the state from which time itself emerges. This is why physicists sometimes describe quantum vacuum emergence as creation from nothing. But this phrase is misleading if taken literally. The nothing here is not philosophical nothingness, but a quantum nothing, a seething, restless field where possibility never dies. Even the ancient idea that something cannot come from nothing no longer holds at the quantum level. The universe may not have violated any laws by appearing. It may simply be an expression of the universe behaving the only way it knows how, by existing. But deeper questions remain. If the quantum vacuum produced our universe, what is the origin of the quantum vacuum itself? Is it truly eternal? Does it exist independently of space and time? Is it a feature of a deeper reality, completely beyond human comprehension? Or could there be multiple quantum vacuums, each generating its own universe bubble? If so, our universe might be one bubble among trillions, perhaps universes with different laws of physics, different dimensions, different fates. Some scientists propose that the quantum vacuum belongs to the multiverse framework. In this scenario, the quantum vacuum is an enormous cosmic landscape where universes form constantly, like raindrops in a storm. Each raindrop is a universe. Some are small and evaporate instantly, others grow into vast cosmic ocean, worlds where galaxies form and civilizations arise. We may be one of those rare drops that expanded, cooled, and stabilized long enough to give life a chance. In this view, the Big Bang was not the beginning of everything, it was simply our beginning. This concept challenges humanity on a philosophical level. If the universe arose spontaneously from a quantum vacuum, then the universe is not a unique miracle. It is a natural phenomenon repeating over and over in the vastness of reality, yet this does not diminish its wonder. If anything, it expands it. The fact that the universe can emerge from quantum fluctuations means existence is woven into the fabric of reality. The universe is not an accident, it is a possibility, an expression of the cosmos's inherent creativity. Still, many physicists caution that quantum fluctuation theory, while elegant, raises difficult questions that remain unsolved. How exactly can quantum fields exist without spacetime? Can fluctuations occur without a temporal dimension to fluctuate in? If the quantum vacuum is timeless, then the word fluctuation might itself be misleading. We may be using human language to describe a phenomenon completely outside human experience. And yet, despite these challenges, the theory remains one of the strongest candidates for explaining the origin of the universe because it fits with what we know about quantum physics and cosmology. Perhaps the greatest insight quantum fluctuation theory offers is this: the universe is not a rigid structure but a dynamic process. It is not a static object that appeared once and remained unchanged. It is a living, evolving system, born from instability, sustained by expansion, and destined to transform. When humans look at the night sky, they are not staring at cold, distant stars. They are witnessing the afterglow of a quantum event that shaped everything they know. In the end, the idea of the universe emerging from a quantum fluctuation invites us to expand our minds beyond comfort. It teaches us that the universe does not have to follow human expectations. It does not have to behave like a story with a beginning and an end. It can emerge from a sea of uncertainty, expand into vastness, and create life. It can grow from nothing and return to nothing. It can be a cosmic heartbeat pulsing in the darkness. And we, tiny beings on a small planet, have the ability to contemplate this mystery, to theorize about it, and to push our understanding of reality to the edge of imagination. 1 second before the Big Bang, according to this theory, was not a moment of anticipation, but a moment without time, without space, where everything that could exist waited silently in potential. Then the universe flickered into being, like a spark catching fire, and from that spark came everything: stars, galaxies, planets, oceans, trees, and the minds that wonder about their origin. The idea that time itself may not exist before the Big Bang is one of the most unsettling, beautiful, and mind-expanding concepts ever introduced in science. It forces us to confront the limits of our intuition because everything we know, every memory, every thought, every physical event, unfolds within time. Time feels so real, so fundamental, so unavoidable that imagining a reality without it seems impossible. Yet modern physics, through both general relativity and quantum cosmology, suggests that time may be a feature that emerged with the universe, not something that existed before it. And if time truly began with the Big Bang, then the question, what happened 1 second before the Big Bang, dissolves into something even more mysterious because the word before loses meaning. There was no before. There was no ticking cosmic clock, no chronological sequence, no unfolding reality. There was only a state beyond human comprehension, timeless, formless, without past or future. To understand this idea, we must first examine how deeply time is woven into human experience. Humans perceive life as a flowing river. Moments pass, one after another. We cannot reverse them, pause them, or escape them. We age in time, we think in time, we love, fear, dream, remember, and hope through the lens of time. Even language reflects this. Every sentence is a chain of events linked by past, present, and future. Time is so fundamental to consciousness that imagining its absence feels like trying to imagine seeing a color no human eye has ever seen. And yet, physics compels us to try. Albert Einstein revolutionized our understanding of time by showing that it is not fixed or absolute. It bends, stretches, and warps depending on gravity and motion. Two people moving differently or standing in different gravitational fields will experience time at different rates. This phenomenon is not theoretical. It has been measured many times. Astronauts age slightly slower in orbit. GPS satellites must account for time dilation to function correctly. Time is not universal. It is part of space-time, a fabric interwoven with space itself. Where there is space, there is time. Where space stretches, time stretches. Where space curves, time curves. And if space has a beginning, then time must share that beginning. This is why the Big Bang is so important. The Big Bang is not merely the explosion of matter into empty space. It is the moment space itself began expanding. Before the Big Bang, there was no space into which the universe expanded. The Big Bang was the creation of space. And if space began then, so did time. Time is embedded in the geometry of the universe. It is not a background stage on which events occur. It is a feature of the stage itself. Remove the stage, and the play cannot exist. Remove the universe, and time itself cannot exist. This idea changes everything. It means that asking what existed before the Big Bang is like asking what is north of the North Pole, or what happens when you travel 10 meters past the edge of a circle. The question assumes a framework that doesn't apply. In everyday life, before makes sense because time flows continuously. But in cosmology, if time begins, then before becomes meaningless. There was no timeline that preceded the universe. There was no ticking cosmic second hand counting down to creation. There was nothing, not because a state of nothingness existed, but because the concept of existence itself only becomes meaningful once time exists. Yet this idea raises its own profound questions. If time began at the Big Bang, what is the nature of the boundary where time emerges? What does it mean for a phenomenon to occur at the very first moment? If there was no time to allow anything to happen, how did the Big Bang occur? The human mind expects cause and effect. We ask what caused the Big Bang, but cause and effect require time. Causes must precede effects. If there is no time before the Big Bang, then the concept of cause breaks down. The universe may simply exist without a cause because the very idea of causation is tied to time. This is one of the reasons the question of origins is so difficult. Our minds are bound to time. We imagine events unfolding, one leading to another. But scientists now consider the possibility that the universe did not begin in a traditional sense. It may not have emerged from anything. Instead, the emergence of spacetime itself may be a fundamental quantum event that simply is. It is not caused, it is not preceded, it is not the result of something else. It is the first moment, and moments before it have no meaning. Quantum gravity theories attempt to describe this boundary between timelessness and time. One of the most famous is the Hartle-Hawking no-boundary proposal. They propose that the universe did not begin with a singular point, but with a smooth transition from a timeless state into a time-bearing universe. In this model, time does not begin abruptly like a light switch turning on. Instead, time gradually emerges, in a way that resembles how space curves around a sphere. On the surface of a sphere, there is no sharp point where the sphere begins. The surface just is. Similarly, the universe may have no boundary in time. It simply emerges smoothly from a state where time does not exist. This timeless state is not a moment before time. It is a different form of existence entirely. Humans struggle to conceptualize it because our thinking depends on sequence. But in this state, there is no sequence. Everything that will ever exist is encoded in a kind of quantum potential structure that does not evolve. It simply is. When the universe transitions into classical spacetime, this potential becomes dynamic reality. The universe begins to unfold. Time begins to flow. The Big Bang becomes the opening note of a cosmic symphony. Another version of this idea comes from loop quantum cosmology, where time emerges from quantum loops of spacetime. In this framework, the universe does not begin from a singularity, but from a previous contraction phase. However, even in these models, time as humans understand it may not extend indefinitely. The compression phase may not be before, In a traditional sense, because time itself behaves differently at quantum scales, becoming discrete rather than continuous. The fabric of reality becomes granular, and time may become something like a sequence of packets rather than a smooth flow. Before the Big Bang in this model is not like yesterday before today. It is a different domain entirely. Another possibility is that time is not fundamental at all. Some physicists argue that time is emergent, something that arises from deeper physical processes. In this view, time is like temperature. Temperature is real, but it is not fundamental. It arises from the motion of particles. If particles stop moving, temperature becomes undefined. Similarly, time may arise from the entanglement or structure of quantum states. If the underlying quantum structure does not support change, then time does not exist. Before the Big Bang, the quantum state may have been static, timeless, without evolution. Once a certain quantum configuration was reached, time emerged as an expression of change. The Big Bang would then be the moment the universe's quantum state allowed time to exist. In this way, time may be a side effect of entropy, the measure of disorder. As entropy increases, time appears to flow. Before the Big Bang, entropy may have been zero or undefined, meaning no arrow of time existed. Without the arrow of time, no past or future exists. The universe would be frozen in a perfect, timeless quantum state. The Big Bang marks the moment entropy begins to grow, giving the universe a direction, a flow, a sequence. The philosophical implications of this idea are enormous. If time has a beginning, does that mean the universe has a purpose? Does it mean there is something outside the universe? If time does not exist beyond the universe, can questions about why have meaning? Humans are wired to look for causes, purposes, sequences, but physics suggests the universe may simply be a self-contained system where time is a property, not a background. The universe does not need a cause any more than a circle needs a beginning point. It simply is. Yet even this explanation does not fully satisfy human curiosity. Our minds rebel against the idea of something emerging from a timeless state. We want to know what set it off. We want to know what triggered the transition from timelessness to time. But again, these questions rely on time-based thinking. Triggering, initiating, and causing all require temporal order. If time does not exist, then nothing can trigger anything. The transition may be part of the structure of reality itself, like a mathematical truth that does not need an external reason. The universe emerges because that is its nature. In the deepest sense, the idea that time began with the Big Bang is a reminder of how small human experience is compared to cosmic reality. We live trapped inside time's arrow, with memories trailing behind us and possibilities ahead. But the universe may not share our perspective. It does not think, react, or exist the way we do. The universe may be timeless at its core, and what we experience as time may be a secondary illusion, a useful one, but not fundamental. Even if time began at the Big Bang, the mystery does not diminish, it deepens. It invites us to explore the origins of the universe, not with simple questions about before and after, but with deeper inquiries into the nature of existence itself. What does it mean to exist without time? What structure does reality take when time is absent? Is timelessness the true nature of the cosmos, and is time merely a temporary condition created by the expanding universe? In the end, whether time began at the Big Bang or emerges from deeper physics, the idea that before may not exist forces humanity to confront the limits of its understanding. It reminds us that the universe is not obligated to make sense to the human brain. Reality does not bow to intuition. It is greater, stranger, and more profound than our instincts allow, and yet we continue to question. We continue to explore, because even if time is limited, human curiosity is not. The universe may have had a beginning in time, but the quest to understand it has no end. Humanity's cosmic curiosity is one of the most mysterious forces in existence, something so deeply woven into our nature that we often forget how extraordinary it truly is. Out of all the creatures on Earth, out of every species that has ever lived, only humans lift their eyes to the night sky and ask questions about the beginning of time. Only humans stare into the darkness of space and wonder where we came from. Only humans look at the glow of distant stars and ask how they were formed, why they shine, and what existed before them. This curiosity has shaped our evolution, our science, our philosophy, and our destiny, and nowhere does it appear more boldly than in the question, what happened 1 second before the Big Bang? This question is not just about physics. It is a reflection of who we are and what makes us different from everything else that lives. The Big Bang happened nearly 14 billion years ago, yet our species arrived only moments ago on the cosmic timeline. Compared to the universe, humanity is astonishingly young. Dinosaurs roamed Earth for more than 150 million years, yet they never looked up and wondered where the universe came from. Ancient fish swam the oceans for 500 million years, but they never questioned what existed before existence itself. And yet humans, having barely existed, dare to ask questions older than the stars. We are not content with sunlight, warmth, food, or shelter. Something in our spirit demands understanding. Something inside us calls us to explore the unknown. Think about how strange that is. Curiosity has no survival advantage when it comes to cosmic mysteries. Knowing the chemical composition of a star does not help you hunt, eat, or avoid predators. Understanding quantum fluctuations does not help you grow crops or build shelter. But still we seek answers. We spend lifetimes searching for truths that do not feed us, truths that do not clothe us, truths that do not shelter us. And yet, those truths matter to us deeply. We climb mountains not because we must, but because they are there. We cross oceans not out of necessity, but out of desire. And we study the universe not because it demands our attention, but because our souls demand it. Humanity's curiosity is a flame that never stops burning. It pushes us to look deeper, think harder, and dream bigger than any species before us. And the question of what existed 1 second before the Big Bang is perhaps the most powerful example of that flame. Because this question challenges everything, the laws of physics, the boundaries of knowledge, even the nature of reality itself. Asking it is like standing on the edge of an infinite abyss and daring to look down. Most creatures avoid the abyss. Humans study it. Our willingness to ask this question reveals a profound truth about the human mind. We are not satisfied with the world as it appears. We want to know what lies beneath the surface. We want to peel back reality layer by layer until we reach the origin of everything. This desire is as ancient as humanity itself. Our ancestors looked at the sky and created myths to explain the sun, the stars, the storms, and the seasons. They built stories to understand what they could not measure. As centuries passed, curiosity transformed myth into observation, observation into science, and science into the powerful tool it is today. Every discovery from fire to the wheel, from writing to rockets, comes from curiosity, and today, curiosity drives us to the farthest edges of the cosmos. It pushes us to launch telescopes into space to capture the light from galaxies billions of years old. It pushes us to build particle accelerators that recreate conditions similar to those just after the Big Bang. It pushes us to design equations that describe the structure of spacetime itself. Humans are the only creatures in the universe, as far as we know, who attempt to reconstruct the moment existence began. This is an extraordinary fact. Even if the universe contains trillions of civilizations, each on distant worlds, our desire to understand the origin of everything remains a defining trait of intelligence. When scientists ask what happened before the Big Bang, they are not merely doing calculations. They are participating in a tradition that began long before mathematics even existed, the tradition of wondering. Wondering is a sacred act. It connects us across time and culture. The first humans who stared at the stars thousands of years ago felt the same awe we feel today. The same sense of mystery, the same burning desire to understand. Curiosity is the bridge that connects every generation of humanity. It makes us part of something larger than ourselves. But what makes cosmic curiosity particularly beautiful is that, unlike hunger or fear or aggression, it is not driven by survival. It is driven by meaning. Humans want meaning. We search for it in religion, in science, in philosophy, in art, in relationships. And the origins of the universe represent the most profound meaning of all, the meaning of existence. What happened before the Big Bang is not just a scientific question. It is an existential one. It is about our place in the universe. It is about whether everything began with purpose or chance. It is about whether the universe is a single event or a repeating cycle. It is about whether time itself is eternal or finite. It is about whether there was a cause, a creator, a fluctuation, or something completely beyond imagination. This question cuts to the core of who we are. Even if science never gives a complete answer, the act of searching transforms us. It inspires us to think beyond our daily concerns. It lifts us out of the smallness of our personal problems and reminds us that we are part of something vast and ancient. When we ask what came before the Big Bang, we are not just asking about physics, we are asking about identity. We are asking what it means to be human in a universe that existed billions of years before us and will continue billions of years after us. Curiosity gives us purpose. Without it, humanity would stagnate. With it, we become explorers of both inner and outer worlds. When astronauts travel to space, when scientists build telescopes, when researchers create simulations of the early universe, they are all participating in the same quest, the quest for understanding. The universe may be silent, but humanity refuses to be. We ask questions, we build tools, we search for answers, even when those answers are beyond our reach. Many people say the universe is vast, cold, and indifferent, but curiosity proves that humanity is not indifferent. We care, we want to understand, we want to connect, we want to know where we came from. In a deeper sense, the question of what existed before the Big Bang symbolizes the infinite nature of curiosity. It is a question with no guarantee of resolution, and yet we pursue it passionately. This willingness to chase the unknown, even when the outcome is uncertain, is what makes humanity extraordinary. We are seekers, thinkers, creators, dreamers. The universe might not give us all the answers, but the journey shapes us. Curiosity teaches us humility, because the more we learn, the more we realize how little we know. It teaches us courage, because searching for truth means confronting the boundaries of understanding. It teaches us unity, because every human being who wonders about the universe is part of the same cosmic story. Curiosity also fuels technological progress. Without the simple desire to understand the universe, there would be no space travel, no physics, no astronomy, no technology, no civilization. Every advancement begins with a question, every question begins with wonder, and wonder begins with curiosity.
This is why the greatest scientists, from Einstein to Hawking, repeatedly emphasized that curiosity is more important than knowledge.
Knowledge is limited, curiosity is infinite, it expands as the universe expands. Interestingly, the question of what existed before the Big Bang may never have a final answer.
And that is okay. The beauty of curiosity lies not in the destination, but in the journey. The effort to understand the universe keeps us moving forward.
It pushes us to challenge assumptions, break barriers, and develop new ideas. Even if the answer remains forever out of reach, the act of questioning enriches humanity. We become wiser, more insightful, more creative, and more connected to the universe. Some people find the idea of an unknowable universe frightening. Others find it inspiring. For many, the idea that time itself might not exist before the Big Bang is not just a scientific possibility. It is a poetic one. It means that the universe is not simply a place, it is a story with a beginning, but perhaps with no single cause. A story that includes galaxies, stars, planets, life, consciousness, and the ability to reflect on its own existence. When humanity wonders about the beginning of time, we are participating in the universe becoming aware of itself. We are the universe thinking about the universe. This is why cosmic curiosity is so powerful. It is not just an intellectual exercise, it is a spiritual one. You do not have to be religious to feel awe when you contemplate the birth of the universe. You do not need to belong to any specific belief system to feel humbled by the vastness of space. Curiosity is universal. It transcends culture, language, race, and geography. It belongs to every person who has ever looked at the night sky and felt something stir inside their chest, something that whispers, "There is more out there, find it." This whisper is ancient. It is the same whisper that drove our ancestors to explore new continents, that inspired early scientists to map the stars, that encouraged philosophers to ponder existence. Today, it drives astrophysicists to analyze cosmic microwave radiation, quantum scientists to study the smallest scales of reality, and engineers to design spacecraft capable of leaving the solar system. But beneath all the science and all the technology, the core remains the same: human wonder. The greatest irony of curiosity is that it reveals how insignificant we are in the scale of the cosmos, yet it simultaneously proves how extraordinary we are as a species. Physically, we are tiny, dust on a cosmic scale, but mentally and spiritually, we reach across billions of light years. We reconstruct the birth of galaxies. We calculate the age of stars. We simulate the earliest fractions of a second after the Big Bang. Our minds travel where our bodies cannot. Curiosity is humanity's greatest superpower. In the end, the question of what existed before the Big Bang is not simply a scientific puzzle, it is a mirror that reflects our nature. It shows us that we are creatures who refuse to accept ignorance as our final state. We push forward. We search, we learn, and even when answers elude us, we continue, because curiosity is not something we do, it is something we are. Humans are the universe, awakened and questioning itself, and as long as we continue to wonder, the journey will never end.